Oh shit, Lauren's gone 2 days. This is, where's my Lauren? It's lecture day 13, right?
Yes.
And today we're prepping for 11.1, which is on exponential functions. And 11.2, which is on logarithmic functions. Hey, Roberto. So,
Yeah, no.
so. Exponential functions have the name word exponent in it. These are functions where the variable is in the exponent. They're called exponential functions. So we can have stuff like f of x equals 2 to the x, 1/3 to the x. Probably the two most common ones are 10 to the x and e to the x. As a reminder, these numbers all down here, or the letter E, are called the base. And things up top are the exponents. This blue pin's dying shortly. So the important thing is, well, some of the important stuff is the base. We don't want it to be negative, so the base should be greater than 0. And base should not equal 1. Because 1 to any power is 1. That gets boring. There's no restrictions on x. For this class, for algebra, we'll stick to real numbers. But you can have complex numbers, stuff like that. See someone on chat. There's Lauren. WTF? Are you not feeling well?
Yeah, I don't feel good. I don't want to get anybody else sick.
Oh, that sucks. I hope you feel better.
Thanks.
Get some chicken soup or something. I used to sneer at that, but it really does like make you feel better. I don't know if it's a mind over matter thing or what. Like you think it's supposed to make you feel better, and hence it does. The shit is real. Fucking some deep shit. You can heal a lot of little minor shit in your body just believing in it. Not everything.
Placebo.
Right, placebo is the placebo effect, but without an actual placebo. So, as let's do a little bit of a refresher on exponent rules. So I'm going to use base A. So we'll have a to the x, the stuff we're gonna talk about. Recall that a to the x times a to the y. When you're multiplying and they have exponents, you add those. And if you're dividing, you subtract. Remember when we got two exponents separated by like a parentheses here, this turns into multiplication, x times y. A to the 0 is 1. These are all rules we talked about already this semester. A to the negative x is the same as 1 over a to the x. And that's actually the same as 1 over a to the x, like that. Some stuff we can do without a calculator. We can do some simple evaluations. Like if I have f of x is 2 to the x. And I want to do like find out f of negative 1, f of 0, and f of 1. This is 2 to the negative 1, which means we can move it to the bottom with the same exponent but positive. And that's just 1/2. By second 0, 2 to the 0 is just 1. And 2 to the first power is just 2. Not too bad. In fact, these are the common ones to check for graphing. When you graph them, if you graph a to the x, you negative 1, 0, and 1, you get 1 over a, 1, and a. Where I'm just replacing the 2 with an a, and that's consistent. I'll give you guys one to try. In fact, I'll give you f of negative 2, f of negative 1, f of 0, f of 1, and f of 2. Try finding those. Anybody got numbers for these? One over 25, that's good. Because that's 1/5 squared, which is 5 to the -2. So 1/25 is looking good. Sarah can speak. I didn't even know this. This is great. Tell me more, Sarah. Now that you're talking. Okay. Ah, shit, this is too easy for you. That's kind of like what we're doing in chapter 11.1 today. We'll go over graphing them, but like you can always do these tables to do them. And you really only need to do these first three to graph them, and then we can do a. Remember how we did all the shifting and translating with the other graphs that we did? The same thing works, the same setup with translations. Moving shit around, and you'll see that a little bit. I did mention E as a base, and I didn't tell you what it was. So I said E to the X is a common one. E is approximately 2.71828. It's called the natural exponent because it shows up in nature a lot. And if you never used it before, you're probably not gonna like it. It's not that bad, you just kind of have to do a calculator with it to do stuff.
Maybe a long time ago, they didn't let the students use it, that would be, they don't have to remember.
Well, that limits what you can ask students. Like I can ask E to the 0 and E to the 1 really easily, but. Even E squared, who's gonna fucking memorize E squared?
Who's gonna memorize pi after the
3.1415926535. I remember I memorized that.
You're-
6th grade one.
You're an exception. I go up to 14159, and that's as far as I go.
I think after that it's like 265358997.
I've seen someone use the numbers in a story. A sequence story about Abraham Lincoln or some shit like that. And it worked, whatever the story was, it followed the sequence of pi. Up to somebody does not place.
My 7th grade math teacher, he had like a little like wraparound thing around the entire classroom. It was just numbers of pi. And I was just fucking off in that class and I was just looking for numbers.
So I had somebody, one of my advisors, when I went to like undergraduate research, you can't really see out there like on this. He had a big old pi symbol right here. And he had 100 inches of pi circling out of it.
Like a tattoo.
Yeah. He's fucking crazy. His last name was Balls. Patrick Balls. I don't know how he was a professor. I don't know how he didn't get fucking more Snickers. It was BAHLS. He was cool. I like him. So you may not like E for a while, but if you go into calculus, you're gonna love E. E is gonna be one of your favorite fucking things when you get to calculus. Because when you start doing stuff in calculus, all the stuff in calculus that changes everything else, E is unfucking phased. E to the X is fucking, you wanna hit me with a derivative or an integral? Fuck off, I'm still E to the X. It's the only one that doesn't change, so it's fucking great. It's named after Leonard Euler. Who used it a lot. So we'll do some graphing in the main course. We're gonna do the compound interest formula, which has variables and exponents. We'll do an example with that, along with the continuously compounding interest formula. And then I want to show you how these connect to logarithms, because logarithms is 11.2. So in 11.2, we do logarithmic equations. And I don't think we discuss it until 11.3, but logs and exponentials are inverse functions of each other. And it goes, it's said like this. This is what it looks like. And the way it's read is y equals log base A of x. That's how that reads. How does it relate to exponentials? This means the same thing as x equals a base A to the y power. The math thing they use for this, they say if and only if. Which is abbreviated IFF. Because we be lazy fucks, and if and only if is a long thing to write when you write it a lot, and they write it a lot in proofs. If means it's a two-way street. You can switch back and forth between them. So a handy way to remember it, the way I remember it is the thing all by itself is the exponent. And the base of the logarithm is the same as the base of the exponent. So base of log and exponent are the same. So you only got to remember it as base once. Those are the two I remember. You can throw in another word if you want. This is like the solution. But remembering the exponent goes on the other side, if I have it written as this, where it's in exponential form and I convert to a log, I put the exponent on the other side and the base stays the same. And there's only three things here, x, a, and y, right? As long as I remember where these two go, the third one doesn't have anywhere else it can go. It's gotta go in the log. Now, a better way of putting that is in parentheses. And I should have done that. They don't always do it. It's a little sloppy to not do it. You should be, it's lazy, basically. It saves time to not do it, but it's helpful. All right, so a couple examples. What examples did we do earlier? I don't want to repeat them. I wrote down, all I did is wrote down 2 and 1/3. We worked with 2 of the eggs. So let's say log base 3 of 9. What does that equal? So if I switch this over to the exponential form, this is my base. In fact, they're all base 3 the way I did it. And all of them have question mark as the exponent. The other side is the exponent, which leaves the thing in the parentheses, what that equals.
So it's what again? It's like the next one, right?
It's an exponent. The way to do these without a calculator is go, how can I write the thing on the right in terms of the number on the left with an exponent? Can I write 9 as 3 to some power? And if so, what power? Second power. Which means question mark has to equal 2. The exponents, when you have the same base, if the bases match and there's an equal sign, exponents have to match also. That's the idea here for equality. This one's a little tricky. Can I write 1 as 3 to some power? If so, what power?
0.
It's the 0 power,
Anything to the 0 power is 1, right?
except for 0 and infinity. That's a calculus topic. So question mark equals 0 here. And what about this one?
3.
Close. 3 cubed is 27. How can I make it so it's on the bottom?
1/3.
We could do it as 1/3 cubed. That would be 1/27,
Right,
but I don't want it 1/3.
I mean like 3 to the power of 1/3.
No, 3 to the 1/3 like this is the cube root of 3. That's not what we're looking for. Close, good idea. Nice to explore some ideas. This is true. Is there a way to get this where the 3's on top? Negative exponent. Throw in a negative. That'll make this up top. So that means now that we have the same base and the same exponent, question mark equals -3. Ready for some more?
Yes.
Oh, Lauren's over here typing in shit. Alright, so we can also solve stuff with this. And the last problem, when we had the right side was our variable, but now here we got the variable in our logarithm. The way to go about doing this is, remember what applies where? That's my base.
Please.
That's the thing by itself is the exponent. Equals the thing inside. So x equals 4. Let's give you guys one.
I thought the y was an exponent. Like, isn't it y equals log base A?
Well, here's y equals 1 in this.
I thought it said x equals. Oh, I see, I was just reading it as log 4 and then x equals 1, that's my fault.
Let's see. Let's give you guys one to try. do you guys get?
1,000.
It's 1,000. Which is 10 cubed. Hopefully you got 1,000. Base 10 is one of our most common ones. It is the most common. And it's based on our numerical system, it's base 10. And that's because most humans have 10 fingers and 10 toes. And so that's how we got good at counting. We used our hands to start doing math, and that's formed a natural basis of our numbering system. It's really convenient for exponents because the 3 tells you how many zeros there are. 3 zeros. Which makes me want to cover the negative version. So I get x equals 10 to the negative 4. So how do I have negative 4 zeros?
Like scientific notation.
Well, yeah, this is a form of scientific notation. A better way of saying this is 3 zeros means move the decimal on 1.0 right 3 times. You're still going to get 1,000 if you do that. What we do when it's negative is move the decimal left. Four times here. So I had 1.0. I can move it left 1, 2, 3, 4. And I gotta fill in empty places with zeros. So 10 to the negative 4 is 0.001.
Want us to put it in decimal form or is like a fraction form good?
I don't know what they're gonna ask you on the homework. Generally, if you can simplify it where it doesn't need an exponent is the better way to do it. That's the general rule.
Well, like I just put like 1/10,000.
That works too. I'm glad you brought that up. Another way of looking at that is at 1/10 to the 4th power, using the negative exponent. And now we can make it look like 4 zeros. So 1/10,000 is the same thing as 0.00001. I think I said too many zeros there, but I have the right number written down. Ready?
Yes.
Calculator talk. You will be allowed a calculator on the test. You are gonna be required to show all your work. The only stuff that really you can't show work for is stuff like logarithms and exponents unless they're very simple. Like the ones we just did, we were able to show all our work. But in general, finding like log base 10 of 3.1. Log base 10 of 3.1 is not something you do by hand. So you can use a calculator on the exam, but it has to be a calculator, not a cell phone.
I bought a few.
If you have a graphing calculator, I don't give a shit. Use the graphing calculator.
Oh, we can skip it over to.
But
So,
you need to show where you got everything. So if you just write down a graph, I'm gonna tell you right now, if each question is worth 10 points, the solution's worth 1.
and.
The work to get it is the important part.
And I was gonna say too, my last class, someone didn't bring a calculator and they were complaining. And so if anybody needs a calculator, just, holler at me. I can bring it on with the calculator. So,
Well, that's nice. I'm gonna have an extra calculator. I'll have a calculator with me. Someone can borrow to check stuff too. You won't, yeah, like most of the numbers, you shouldn't need a calculator to do. They should be on the times table. Or like if there's a square root or a cube root should be someone like one of the simpler ones. But like you can always check it for that. On a calculator. Mine are hidden. Let's see if I can show this. I'm going the wrong way. See where it says log and then it looks like IN? Over here? My 10 to the X and E to the X are right above it in yellow. So I have to do a second shift button. My shift button up here is in yellow. So if I want to access the exponent keys, I have to use shift. They deliberately put them for me directly over the log that corresponds to them. Your calculator probably does something similar. Mine shows 10 to the X above this and E to the X above this. When we say log, and there's no number listed like log X, it implies log base 10 of X. So there is a hidden, it's not depicted, 10. We just say log X because it's the common one. In fact, we call that the common log. If you're gonna, the name for it is common log. When you see natural log or ln, this is an ln, but it's a lowercase l. Log base e of X is the same thing as ln of X. So ln implies base e. Does everybody have a calculator with them? Let's what? All right, let's walk through some. Let's find I said 10 to the 3.1, let's do 10 to the 3.1. So on my calculator, let me not write over the calculator over the text while you guys are still writing. So I'm gonna hit shift on my button, my calculator, and hit the 10. And notice that a 10 appears in a little window. I think I can directly put in, I wanted 3.1. And I don't need a parenthesis sign. It might make it easier to read. This is the same thing as shift 10. Okay, shift parentheses 3.1. That makes it a little bit easier to read. That is 1,258. .925412. Play around with your calculators until you get that. Make sure you get that. And then let's do e to the 3.1. So I do shift and then the LN button.
22.1975128.
22 point, that sounds like what you said. 19795.128.
Yes. Will not be moving.
What about log of 3.1 and ln of 3.1?
Oh, God. 49136.
So then I got 1.131402. 1.131402.111. Yeah.
You guys got those four answers, you know how you use it, how to use the calculator. And this will help you find any other base. Because there's a formula called the change of base, but it's already back in 3 o'clock. We'll talk about change of base in the main class.
Why is it like for when you press log, why is it always just log base 10 when you need to do something where it's not base?
We'll do the change of base formula. You'll see in the next chapter, or when we start the next lesson. Actually, I'll just show it to you real quick. I change it for log base A of X. You can do log base B of X divided by log base B of A. And so picking B equal to 10 or E allows you to use the calculator. So like log base 2 of 7 is log 7 over log 2. Or ln 7 over ln 2. You get the same thing either way. I'm gonna hit stop record.